case, the pictures of Alan Turing labeled with the text that we would want the computer to produce. If I showed you this picture, I would want you to produce the text Alan Turing. Okay. Training data is important. Every time you go on social media and you upload a picture to social media and you label it with the names of the people that appear in there, your role in that is to provide training data for the machine learning algorithms of big data companies. Okay? So this is supervised learning. Now, we're going to come on to exactly how it does the learning in a moment. But the first thing I want to point out is that this is a classification task. What I mean by that is, as we show it the picture, the machine learning is classifying that picture. I'm classifying this as a picture of Michael Wooldridge, this as a picture of Alan Turing, and so on. And this is a technology which really started to work around about beginning 2005. It started to take off, but really got supercharged around about 2012. And just this kind of task on its own is incredibly powerful. Exactly this technology can be used, for example, to recognize tumors on X-ray scans or abnormalities on ultrasound scans and a range of different tasks. Does anybody in the audience own a Tesla? A couple of Tesla drivers, not quite sure whether they want to admit that they own a Tesla. We've got a couple of Tesla drivers in the audience. Tesla full self-driving mode is only possible because of this technology. It is this technology which is enabling a Tesla in full self-driving mode to be able to recognize that that is a stop sign, that that's somebody on a bicycle, that that's a pedestrian on a zebra crossing, and so on. These are classification tasks. And I'm going to come back and explain how classification tasks are different to generative AI later on. Okay, so this is machine learning. How does it actually work? Okay, this is not a technical presentation, and this is about as technical as it's going to get, where I do a very hand-wavy explanation of what neural networks are and how do they work. And with apologies, I know I have a couple of neural network experts in the audience, and I apologize to you because you'll be cringing with my explanation, but the technical details are way too technical to go into. So, how does a neural network recognize Alan Turing? Okay, so firstly, what is a neural network? Look at an animal brain or nervous system under a microscope and you'll find that it contains enormous numbers of nerve cells called neurons. And those nerve cells are connected to one another in vast networks. Now, we don't have precise figures, but in a human brain, the current estimate is something like 86 billion neurons in the human brain. How they got to 86 as opposed to 85 or 87, I don't know. But 86 seems to be the most commonly quoted number of these cells. And these cells are connected to one another in enormous networks. One neuron can be connected to up to 8,000 other neurons. Okay, and each of those neurons is doing a tiny, very simple pattern recognition task. That neuron is looking for a very simple pattern, and when it sees that pattern, it sends a signal to its connections. It sends a signal to all the other neurons that it's connected to. So how does that get us to recognizing the face of Alan Turing? So Turing's picture, as we know, a digital picture, is made up of millions of colored dots, the pixels. Yeah, so your smartphone maybe has 12 megapixels, 12 million colored dots making up that picture. Okay, so Turing's picture there is made up of millions and millions of colored dots. So look at the top left neuron on that input layer. So that neuron is just looking for a very simple pattern. What might that pattern be? It might just be the color red. All that neuron's doing is looking for the color red. And when it sees the color red on its associated pixel, the one on the top left there, it becomes excited and it sends a signal to all of its neighbors. Okay, so look at the next neuron along. Maybe what that neuron is doing is just looking to see whether a majority of its incoming connections are red. Yeah? And when it sees a majority of its incoming connections are red, then it becomes excited and it sends a signal to its neighbor. Now remember, in the human brain, there's something like 86 billion of those, and we've got something like 20 or so outgoing connections for each of these neurons. In a human brain, thousands of those connections. Yeah? And somehow, in ways that, to be honest, we don't really understand in detail, complex pattern recognition tasks in particular can be reduced down to these neural networks. So, how does that help us in artificial intelligence? That's what's going on in a brain in a very hand-wavy way. Okay, so that's obviously not a technical explanation of what's going on. How does that help us in neural networks? Well, we can implement that stuff in software. The idea goes back to the 1940s and two researchers, McCulloch and Pitts, and they are struck by the idea that the structures that you see in the brain look a bit like electrical circuits. And they thought, could we implement all that stuff in electrical circuits? Now, they didn't have the wherewithal to be able to do that, but the idea stuck. The idea's been around since the 1940s. It began to be seriously looked at, the idea of doing this in software, in the 1960s, and then there was another flutter of interest in the 1980s, but it was only this century that it really became possible. And why did it become possible? For three reasons. There were some scientific advances, what's called deep learning. There was the availability of big data, and you need data to be able to configure these neural networks. And finally, to configure these neural networks so that they can recognize Turing's picture, you need lots of computer power. And computer power became very cheap this century. So we're in the age of big data, we're in the age of very cheap computer power, and those were the ingredients, just as much as the scientific developments, that made AI plausible this century, in particular taking off around about 2005. Okay, so how do you actually train a neural network? If you show it a picture of Alan Turing and the output text Alan Turing, what does the training actually look like? Well, what you have to do is you have to adjust the network. That's what training a neural network is. You adjust the network so that when you show it another piece of training data, a desired input and a desired output, an input and a desired output, it will produce that desired output. Now, the mathematics for that is not very hard. It's kind of beginning graduate level or advanced high school level, but you need an awful lot of it. And it's routine to get computers to do it, but you need a lot of computer power to be able to train neural networks big enough to be able to recognize faces. Okay, but basically all you have to remember is that each of those neurons is doing a tiny, simple pattern recognition task. And we can replicate that in software, and we can train these neural networks with data in order to be able to do things like recognizing faces. So, as I say, it starts to become clear around about 2005 that this technology is taking off. It starts to be applicable on problems like recognizing faces or recognizing tumors on X-rays and so on. And there's a huge flurry of interest from Silicon Valley.